Okay, so welcome to the Oxford Discrete Maths and Probability Seminar. This week it's a great pleasure to have Elchanan Mossel, who's going to talk on, well, you can see the slide, revisiting Jerrum's Metropolis process for the planted Clique problem.
So I have to press got it after the recording. Okay. Thank you very much for the invitation. I mean, I don't like usually to give Zoom seminars, but you know, this is a great forum, and I'm happy to give a talk. So we had a short discussion with David, you know, maybe about why am I giving this talk. So I thought of giving this talk about because of, you know, Jerrum, you know, is based in England, and I think David said that, you know, actually he mentored Jerrum many years ago, David Aldous. So there's the British Markov chain connection here, and this talk. I hope you're gonna like it. It's sort of a you know a newer view on an older problem that we're going to look at. So let's start. Okay, so for this audience, I'm sure I don't have to recall what's the Erdős-Rényi random graph, but let me do it anyway. So the Erdős-Rényi random graph is the most classical random graph. You have n vertices, and each potential edge is connected with probability 1/2 independently. What we're interested in this talk is about cliques in this graph and variants of this problem. So a very simple application of the probabilistic method, maybe the first or second moment, will show you a very classical result. Shows that the maximized the clique of the maximized size is of size about 2 log n, so 2 log n times 1 plus little of 1 with high probability. We're interested, or the interest in the hidden clique in the clique problem is maybe the algorithmic problem of finding such a clique. And somehow, interestingly, all the algorithms that we know only finds cliques of size which is about log n. So you know, there's the difference again. It's 1 plus little of 1. This is not up to constant. So there's a difference between the maximal clique, which is of size about 2 log n, and what we call efficient algorithm that find it in times log n. We find cliques of size log n. And just maybe to make the comment in the last line that you see here, this is not the kind of problems that we're used for in computational complexity, where you know the best known algorithm are maybe exponential time. There is an algorithm that finds a cliques of size 2 log n in times which is essentially n to some constant times log n, because you can just enumerate over all potential cliques and see if they're cliques or not, and that's you know, would take times n to some constant log n. So the distinction here between efficient and non-efficient, it's really between n to some fixed power and n to some power that you know diverges to infinity, but it diverges, you know, it diverges in this case not faster than log n, right? So the natural question, you know, when we think about maybe algorithm is, you know, can we find these bigger cliques? Can we find a clique of size 1.1 log n in this GN 1/2? So any questions so far? And I have to apologize. This is actually, you know, most of the slides. So I forgot to say many things. So this is joint work with Zongchen, Chen, and Iias Zadik. And actually, Zongchen, Chen make a sort of a version of the slides that I'm playing off. And this is the first keynote lecture I'm ever giving. So maybe if you see the technical, how technical savvy I am, it's because of that. Okay, so we are talking about Markov chain Monte Carlo, and Jerrum in '92, you know, Jerrum and later Jerrum and Sinclair did some very fundamental work on Markov chain Monte Carlo, and he considered the Metropolis algorithm for finding a clique that's a little bigger than log n in this Erdős-Rényi random graph. So let me walk you through this algorithm. So it's a Markov chain algorithm. So you start from some starting point, like many algorithms. Actually, the starting point is not completely trivial because we want to start from a clique. So a clique is just a collection of vertices, all of the edges between them exist in the graph. And you know, starting from a large clique is not necessarily an easy task. That's sort of what we want to do. But you can also start from a small clique, like the empty clique. And the rule of the Markov chain is at time t, you generate xt from xt minus 1. Xt is the time, the clique at time t from the clique at time t minus 1 in the following manner. You pick a vertex uniformly at random. So this is the vertex uniformly at random among all the vertices in the graph. And if the vertex that you chose is not in your current clique, then you try to edit. So you edit, you expose all the edges between the new vertex and the existing vertices in the clique. If it is a clique, you're happy, you join your vertex to the clique. If it's not a clique, you do nothing. You try the move, you try the Metropolis move of adding this vertex, and if you failed, you do nothing. And if the vertex is in the clique, then with some probability, that depends on the parameter, that depends on the temperature if you want. With some probability, you remove this vertex, and otherwise you keep the vertex the same. And sort of with analogy to the statistical physics model, we call this parameter of this probability of removing the vertex e to the minus beta, and beta is sort of a free parameter that we may choose in any way we want. Any questions on this? This is a very simple Markov chain. You don't want to be greedy. You don't want to always go up. You want to explore the space a little bit. So sometimes with some probability you go down, just in case you're sort of in the wrong part of the space, and you hope that by exploring the space this way, you will be able to find a big clique. So let's see how it plays out. So what you see is an example of this algorithm. We have the graph that we've seen before. And our current clique are the 3 red vertices. And now I'm choosing a vertex uniformly at random. I'm trying to look at the 3 potential edges. Of the 3 potential edges, only one is in my Erdős-Rényi random graph, so it's not a clique, so I'm staying at where I was. Then maybe I pick this vertex. This vertex has connected to all vertices in the current clique, so I can edit if I can edit, so I'm going to edit. So now my clique is this. Now maybe I pick one of the vertices in the clique. And then the rule says that with some probability e to the minus beta, I remove this vertex from the clique, and otherwise I keep it the same. Questions on this? Okay, so very, very, very natural algorithm. And the choice of the parameters, and if you think about it, like many times Metropolis algorithms, is reversible, and the stationary, it's reversible with respect to a very simple stationary distribution. And the stationary distribution, the probability of any clique is proportional to e to the beta times the number of vertices in the clique. Okay, so if beta is positive, which it is in our case, it puts more weight on bigger cliques than on smaller cliques. So you can check that it satisfies the detailed balance equations with this probability distribution. That's what one of the reasons of defining this algorithm. So of course, what it means is that if beta is 0, we get a uniform distribution over all cliques of all sizes. If beta is of order constant, and if you sample from this distribution and you do the analysis, you would see that actually you sample cliques of order size log n. This is where sort of the algorithms get stuck. And once you start getting to beta to be bigger, maybe you look at betas which is of order log n. And then if you sample, you actually get cliques of size that is slightly bigger than log n. So you can, by setting the constant appropriately, maybe you can get 1.5 log n in front of the log n in the temperature in beta. So what is the hope, or what was Jerrum's hope? So I'm still telling you a story from 30 years ago. So the hope is that somehow xt converges to pi quickly, and we get a clique of size that's bigger than log n, and then we're happy we beat sort of other algorithms that only get cliques of size log n and not say 1.1 log n. So here's what Jerrum proved already in the 90s. For any beta, beta might not be a constant. It might depend on n. It might be log n, for example. NP stands for the Metropolis. Metropolis finds to find a clique of size 1 plus epsilon log n. And here is the twist. So not only it fails even if we plant a large clique of size n to the 1/3 or n to the 0.499, n to the alpha for any alpha less than a half. So Jerrum said, not only this algorithm fails, it also fails if I make the problem easier. How am I going to make the problem easier? I'm going to make the problem easier by actually adding to this Erdős-Rényi random graph one big clique, one clique of size n to the 1/3. Questions on this? Okay, so this is Jerrum's result. It's sort of very strong failure of an algorithm. Not only does it not find cliques of size 1.1 log n, it even fails if you add to the graph a huge cliques of size n to the 0.49. So let me talk a little bit about the planted clique model. So the planted clique model was actually introduced independently in these two papers, in this paper by, two of the classical point of reference are these papers of Jerrum from 92 and Kuchera from 95. And the model is the following model. It's the model we just talked about. So you start from G0. That's step one. G0 is an Erdős-Rényi random graph. And then you pick a subset of k vertices uniformly at random. You add a clique on these k vertices, and your graph is the union of edges, the original Erdős-Rényi random graph, on the clique on these random k vertices that you chose. Okay, so sorry, in this picture, I add a clique. Now I add all the edges between them, and that's the graph that I'm seeing. And again, maybe a different algorithmic task than the one that we talked about before. Before we just wanted to find a big clique. Now maybe we have a more ambitious or a different goal. The goal is to recover the planted clique from this new random graph. So again, this new random graph is a standard Erdős-Rényi random graph is edge probability 1/2, union with a clique of size k, where the k vertices are chosen uniformly at random. And of course, when you think about this problem, is you say, well, how large k needs to be so I can do it, and when can I do it efficiently? Questions, anyone?
Hi, can I just check I understand what Jerrum's result was? So when you say it fails to find it, that means if you fix any polynomial amount of time, it won't find it within that time with high probability or something. Is that what?
Right. So yeah. So I didn't set it completely formally, but what he actually proved is it proved that you will not hit any clique of size 1 plus the hitting time of a clique of size 1 plus epsilon log n. If you start from the raw starting point or from a random starting point from a certain distribution, is more than any polynomial.
Cool. Okay.
In fact, it's n to the some constant log n.
Great.
Okay. Good. Excellent question. More questions? Thank you.
Yeah, another quick question. So in Jerrum's result, I think the starting condition also has to be past the log n barrier, right? In his
Say again?
In Jerrum's results.
Yeah.
The initial condition is already past the log n barrier, isn't it, in his paper?
What do you mean the initial condition? Where you start the clique?
Yeah, exactly. So yeah, your initial.
Well, the starting of the algorithm. So I'll talk about. Actually, I'm going to talk about the starting point in a little bit in more detail, right? So it's actually drawn from some distribution. I'll explain in a little bit what actually. So I'm going to talk about Jerrum's result in more detail in a little bit. So hit me again if I don't answer this question. Okay, so we did this. Okay. Sorry. More questions. Sorry, I'm still playing with the slides using Keynote. More questions? Okay. So let me tell you a little bit about this hidden clique problem. So the goal again is to recover this planted clique from observing this graph union, the clique, and let's just talk about what can you do, right? So information theoretically, it's not hard to show. This is the simple algorithm that we said before, that if you plant a clique of size 2.1 log n, you can find it just by enumerating over the clique. Everything I'm saying is with high probability. So with high probability, you're not going to be confused by the Erdős-Rényi random graph. If you have a clique of size 2.1 log n, you're going to enumerate, you're going to find it. It's going to be the only one, and you're going to find the planted clique, right? So in terms of algorithms that run in more than polynomial time, you can do it as soon as the planted clique is bigger than 2 log n. Now, if you look at a clique that's much, much bigger, let's say your clique is of size n to the 0.6, and you think about it a little bit, you just say, how am I going to find the clique with high probability? Everything that we're talking about with high probability, we're going to say, well, I'm going to look at the degrees of nodes. And the degree of a node in Erdős-Rényi random graph is n/2 plus standard deviation of order square root n. But in the clique, I have more neighbors. Now I added this n to the 0.6. So, this degree of the vertices in the cliques are going to be all bigger. I'm just going to look at all large degree nodes, and I'm going to find my cliques. So this is a very easy analysis. So you can call it poly-n algorithm, but it's a very fast algorithm. Essentially, you just have to count the degrees of all the vertices, and you find the cliques. So log n is sort of difficult. Once you're slightly above square root n, it's very easy. And then that's essentially all that we know. Once you want to lose this square root log n factor, you have to work harder. And some very good people have tried to beat this square root n barrier. But the best method that we have just gets square root of n. And here you have to do something more sophisticated. If you cannot, if you're really at, your clique is of size, say 2 square root n or 4 square root n. So there are various methods that are more global. I'm just going to mention what they are. Maybe the first one by Alon, Krivolevich, and Sudakov is using the eigenvalues of the adjacency matrix. Then these days there's approximate message passing and many other methods. And what people observed is that when the size of the clique is little of square root of n, many algorithm fails. One is what we mentioned right now is the Metropolis algorithm. That failed for cliques of size less than square root of n, but other more modern method of trying to understand failure of algorithm for statistical problems, such as the sum of square hierarchy, or things that are used on statistical queries, also fail in this regime, right? So it sort of looks like, of course, we don't really know how to prove any, or for many problems, we don't know how to prove that they require more than polynomial time. But it seems like some of the methods that we do have that are more sophisticated, like sum of square or the statistical query algorithm, breaks exactly at the square root n barrier. So sort of a picture that emerges these days is the following picture. So what you see on the x-axis is the size of the clique that we plant. So we are at gn1/2. We plant a clique up to the 0.2 log n. When I say impossible to recover, I mean it's information theoretically impossible to recover. It's just like no matter for how long you run, it's just like there's contiguity result. If you want, you cannot really recover between 2 log n and essentially any constant square root of n, or between 2 log n and let me write any square root n. You can do it for any constant in front of the square root n with more and more time. So between 2 log n and constant square root of n, it's a conjecture to be computationally hard by many. And above square root of n, there's many efficient algorithms. And even though this, might look as a curiosity, I mean, I think there was quite a bit of work in trying to find efficient algorithm for finding this hidden clique for cliques of size little of square root of n, and sort of none of them were succeeded. And what happens, like many times in the computational sciences, it became a standard assumption to assume that finding a clique of size little of square root of n is hard to do in polynomial time. And in fact, what people do these days is to say, assuming this is hard, I'm going to show that some problems in compressed sensing, or in sparse PCA, or in property testing, or in cryptography are hard, right? So it became sort of a basic module that you reduce to in order to show that all of these problems in applications areas are hard, assuming that this is hard. Okay, so any questions about this? So now I want to actually start talking about the math that's going on here. Any questions about the sort of high-level picture? Okay, so again, we have a clique of size n to the alpha, and so alpha is some power between 0 and 1. We said that the stationary distribution, it's reversible with respect to the stationary distribution, which is the probability of a clique is proportional to e to the beta, the size of the clique, the number of vertices of the clique. And what I want to say is that for every alpha that's positive, if you look at this probability measure, and if you look at the sample that you sample from this measure, then for such cliques, because you have this big hidden clique, if you sample from this measure, with high probability, you are going to get a clique that you sample inside the hidden clique. And this is just a counting argument. I mean, it's not actually the counting argument that we have here. In this more naive counting argument, we're just counting the number of cliques inside the planted clique versus the number of cliques that completely outside the hidden clique. But if you do a more detailed counting analysis, that you can see that, in fact, the stationary measure is supported on cliques that are inside the hidden clique. So, and the hope is that, xt converges to pi in polynomial time, and we see this way, we see a big proportion of the clique. And again, now I'm going to state Jerrum's result a little more formally. For any power alpha less than a half, and any temperature beta greater, or any parameter beta inverse temperature greater or equal than 0 can depend on n. The Metropolis requires time that is n to the power log n to get to 1 plus epsilon log n clique under the worst case initialization. Okay, so like in many results in Markov chain, we don't actually know how to prove it, under an initialization of the type that we like. We just know how to prove it under worst case initialization. Okay, so now we want to maybe improve on this result and think what can we do better, and so that's what we want to talk about. So here are the three questions that we want to answer in this talk. So why alpha less than a half? Okay, so Jerrum in his paper asked, I succeeded to show that it fails for alpha less than a half, but what happens between alpha equal 1/2 and 1? So maybe seeing all these other algorithms that work for alpha bigger than a half, you'd expect that it works also for alpha bigger than a half, but Jerrum didn't conjecture that. Even though I think other people who read Jerrum paper sort of viewed it as the first evidence of the hardness of the planted clique problem when the size of the clique is smaller than square root n. Why are we just interested in finding cliques of size 1 plus epsilon log n? Maybe if you think as an algorithm designer, if you want to find the hidden clique, maybe you just want to find a clique that contains a lot of vertices from the hidden clique. So maybe you want to find 0.2 log n vertices from the hidden clique, and then there's a way for you. There are actually ways to use that in order to look at some sub-problems and maybe get the hidden clique from that. So maybe instead of this barrier of just 1 plus epsilon log n cliques, you're actually interested in the intersection between the clique that you found and the planted clique. And of course, the last question is why we assume the worst case in initialization. It's kind of weird to assume the worst case initialization, because probably when you run the algorithm, you cannot even find this initialization, right? Like somebody said, if the worst case initialization might be a clique of size 1.2 log n, I don't even know how to find this, 1.2 log n size clique. So what does it mean, right? What I will do in practice, probably start from the empty clique, or a clique with 3 vertices, which is very easy for me to find, and I'm going to run the algorithm from there, right? So this is definitely looks like a deficiency of the result. Okay.
Can I ask a quick question? Yeah. The other question that comes to mind is, why is beta constant? I mean, in practice, wouldn't you sort of tune beta like as a function of the size of the current clique, something like this?
So you can do that, of course. This is a very good question, and now you're going to the work of simulated annealing or tampering and swapping. And swapping, there are algorithms like that. So I'll say two things about this. One, this is a little bit, once you start changing the beta as a function of the temperature, it means that you're working with many probability measures simultaneously, and this is sort of in general hard to analyze. But I would say that some of our results actually work for some versions of tempering and swapping, right? So, maybe I'll mention it at the end if we have time. So there are algorithms that, maybe don't just keep one copy of the clique and one temperature, but keep many copies. And there are some, and each of them is at a different temperature, and then you play with this. So we did look at that, and some of our results carry on to this kind of algorithms. But I just for others, I know that but for others, I would mention beta can depend on n in all of the results that we're talking about. Okay, so here's what we proved. So we answered some of these questions. We answered most of this question, and one would say all of this question except for one caveat. So, first of all, we were worried about the fact that the clique was of size at most square root of n. So in fact, for any clique that is sublinear, any n to the alpha where alpha is less than 1, the Metropolis algorithm requires a super polynomial time to reach a big clique, or even a clique that has intersection gamma log n with the planted clique, where gamma is any constant bigger than 0. So even to get intersection 0.001 log n with the planted clique requires super polynomial time. And our results, like Jerrum results and many results in the Markov-Chen literature, are under a worst case initialization for any beta that may depend on n. And interestingly, we also prove it under maybe the most natural initialization, which is the empty clique. But there we cannot prove it for all beta. We can only prove it either for beta that's little of log n or beta that's omega of log n. Somehow beta that's exactly like 5 log n, a constant log n, we do not know how to prove that. So, if we have time, maybe I'll have time to talk about this. Okay, so what does it say? It says that, Metropolis is not good for the planted clique problems because there are other algorithms that find planted cliques when it's of size n to the alpha and alpha is bigger than 1/2. And it's kind of historically, I think one of the reasons I like this story so much, it's sort of a weird twist, right? So part of the reason that people start believing in this hidden clique problem is this result of Jerrum that says that Metropolis fails for finding hidden clique when it's of size less than square root of n. But in fact, Metropolis fails find hidden clique even if it's of size n to the 0.8. But historically, it might have been the good trajectory because somehow the fact that Jerrum proved what he proved maybe made this question about the hidden clique so interesting, and now we really have some, interesting connection to other areas, while the failure of Metropolis is sort of, something that has nothing to do with the real difficulty of the hidden clique problem. Okay, so I want to tell you a little bit about the proof. I will a little bit about our proof. So I should say that I don't know if it's good or bad, but we didn't invent any new, essentially new technology, right? So everything that we do is using very standard methods of Markov chains that that we learned from Jerrum and from Erdős and from others. We are using this very basic idea of a bottleneck argument or Cliques's inequality. So what we want to do is we want to find a set that's big in measure such that its boundary with respect to the move of the Markov chain is small. In particular, we want to find a set such as the probability of the boundary of the set divided by the probability of the set is less than 1/n to the log n. And we know that if we if we find such a set, then the Metropolis algorithm will require n to the order log n time to escape the set A. And the worst case starting point is not really a worst case starting point, but it's kind of a worst case starting point. It's when we start from the uniform, the stationary distribution by condition on being on the set A. So that's a completely standard argument in Markov chains. The only thing that we do here is maybe we are more careful in choosing what the sets A that we're looking at are. And that's the argument also that Jerrum used in his paper. This is the classical way of thinking about this problem. It's really the geometric way of thinking about Markov chain. It's really the details of how do you choose the set A that are different here. So a very natural thing to look at is maybe maybe I'll say first in words what's the new aspect is. The new aspect is sort of we're looking in 2 axes simultaneously. I think sort of Jerrum paper just sort of looked at the size of the clique, while we are looking both of the size of the clique and of the size of the intersection, right? So in this example, maybe A is the set of all cliques whose intersection with the planted clique is of size at most gamma log n, and then of course the boundary is when the size is exactly gamma log n, assuming this is an integer. And what can we show? So maybe even before we introduce the beta, we just look at the counting. We just look at this corresponds to the case beta equal to 0. We can show that these things are concentrated for appropriate values of gamma, and not for large values of gamma, but for appropriate values of gamma. They are both, this is a random graph, right? We remember everything is a random graph, so we can count. We can do the force moment. We can look at the size of the set A in expectation, the size of the boundary of the set A in expectation, and they're both concentrated enough so that they with high probability they behave as they should. So if we look at beta equal to 0, we just count the number of cliques of various size, we get the bottleneck that we want. So this gives us the result for beta is equal to 0, as I just said. And for general beta, it's a shame I don't know how to point here, but for general beta, I'll walk from the left to the right. So we want to understand. The ratio, this bottleneck ratio for general beta, and the basic idea is that we sort of look at, like I said, this more detailed information, which includes both the size of the intersection. These are the set that are indexed by both Q and R, which include both the size of the clique and the size of the intersection. And we're saying, what we want to understand is we want to understand the sizes of the set that have intersection exactly, say, gamma log n. So this is up to small polynomial factor up to factor n. It's like the maximum of this, or actually log n. It's the maximum over the size of the possible clique that you're looking at. And then you have e to the beta q. And then you have cliques of size q that have intersection gamma log n. And then at the bottom, you do the same. You say, I'm going to divide by all possible values of the size of the clique, and I have this e to the beta q. And the reason, of course, I'm doing this maximum is then I do this maximum over maximum. Again, I'm losing just polynomial factors. When I'm using this maximum over maximum, the e to the beta q disappear, and I'm back in the situation. I'm actually just counting the number of cliques of various sizes, right? So that's sort of the basic idea of what we're doing. And really, the way we deviate from what Jerrum did is just including this extra parameter, which is the size of the clique and the size of the intersection. So, so this is that. No, sorry. Okay. So sorry again. What's happening here? So let me say a little bit about the comparison with the original Jerrum's argument. So Jerrum argument was based on, again, using some bottlenecks, like as somebody says that, slightly the bottlenecks themselves. Okay, so I should say this is related to the question that somebody asked before. The bottlenecks themselves are defined in sets in terms of cliques that are slightly bigger than log n. What it says about sampling from the measure condition on that, I think it's right that most of the guys that you're going to sample are going to be a little bigger than log n. I have to think about it more carefully. But he defined it in terms of cliques of size slightly bigger than log n that are expandable, that you can make them a little bigger. You can go from almost 1 plus maybe epsilon over 2 or 2 epsilon over 3 log n. You can add a few more vertices to get bigger cliques. And this argument only works when alpha is less than a half. And the reason is that when alpha is bigger than a half, then actually, if you look at this bottleneck, then in fact, almost all of the cliques that we're talking about are inside the hidden clique. Right. So right. And sorry. So let me try to explain again the context of what we're doing. What we did in the previous slide is we explained the proof of why we don't get a large intersection with the hidden clique. Now what we're doing in this slide is we explain why don't we get a large clique, right? So as I said, let me recall there are two results. One is that you don't get to a 1 plus epsilon log n size clique, which is what we're talking about right now. And what we did in the previous slide, the slide about the intersection, is just to show that you cannot get an intersection of 0.01 log n with the hidden clique. And our proof for the fact that you don't get cliques of large size uses a combined bottleneck. Sort of says, when you start, you're going to look at the set A intersection B, right? So you're looking at cliques that have small intersection with the hidden clique, and that are inside this expandable set, and these cliques are going to have a small boundary. Okay, so again, the easier result to just explain why you don't have a large intersection with the hidden clique. To actually prove that you don't have a large clique, we used a slightly more refined bottleneck argument that takes into account both the fact that both the original Jerrum bottleneck and we take the size that of not the side of the hidden clique of this bottleneck and the intersection with our bottleneck that doesn't contain the hidden clique, and that's the set of cliques that have a small intersection with the hidden clique. A question about this. So sorry, this was a little fast, but questions about this. Okay, so I want to talk a little bit about the empty clique initialization, and maybe I think this is essentially my last slide, and maybe if there's depending on the questions, I will move to the iPad and I will give you a little bit more details about this proof if you wish. So I want to say, how do we? So I said that some of our results we can also prove when we start from the empty clique, which is possibly the most natural initialization for this problem. And I mean. So I told you there's sort of, we know how to prove it in two cases. We know how to prove it when beta goes much slower than log n, and we know how to prove it when beta goes much larger than log n. And when it goes much larger than log n, it's not really, if you look at what happened, it's not really a Markov chain. It's just a greedy algorithm, because you never, if you actually compute, you see that you will never remove a vertex. So you just, you pick a random vertex, you try to add it. If it adds, you get a click, you continue, otherwise you don't. You never remove any vertices. And analyzing this kind of algorithm, you can imagine it's not too hard. You start from something that's empty, sort of go in a random direction, then you get stuck, right? So this is sort of what analysis shows. The more interesting proof, which, if I have time, after some question, I can try to explain more on the iPad, is what happens when beta is as little of log n. And then it turns out that actually you can analyze it essentially by comparison to a burst and test process, just looks at the sizes of the cliques. So essentially you can show that the sizes of the cliques, even though this in itself is not a burst and test process, you can couple it to a burst and test process, and this coupling to the burst and test process will show you that it takes a lot of time to if you start from the empty clique to hit either a clique of large size of 1 plus epsilon log n or a clique that has a large intersection with the hidden clique. So, like I said, I'm going to, if there's more time, I don't know how much time I have. If more time, I can give you more details on the iPad. And again, so our results are compared to Jerrum. We get that Metropolis is bad for hidden clique even for alpha less than 1, and bad meanings that it doesn't find a clique that's of size 1 plus epsilon log n. It doesn't find a clique of size 0. Or epsilon log n that has intersection on epsilon log n with the hidden clique. And it's true under worst case initialization, and except for a knowing range of betas, it's also true when you start from the empty clique. So I think that we, like I said, I think we enjoyed this project a lot. I don't think we discovered any essential new general tools that we can apply. We use bottlenecks, and we use burst and test processes, which have been used before in the theory of Markov chains. But the questions, the big questions that we see remaining is one. I think we believe that Metropolis fails for any beta. Log n is kind of an interesting case where we don't really understand what's going on. And in our bottleneck, we don't gain anything, but we don't really understand what's going on. And of course, it's been open for many Markov chains to prove lower bounds that are not just based on sort of a random state, but are working for very natural initializations. And of course, there's the big problem, just understanding the planted clique problem. Can we find MC algorithm that get all the way to square root n? Are there more efficient algorithm for the hidden clique, and so on and so forth? So I think maybe I'll stop here for questions. Then you can tell me how much time we have, and then maybe I'll talk a little bit about the empty initialization if there's time.
Thank you, Elchanan. But we got 15 minutes or so there's certainly time for you to give us some more details. We can also ask a question or two.
Okay, sounds good. So maybe ask questions first, and then I'll move to the iPad. Yeah, are there any questions until now? Before I move to different technology.
So I had one question. The Metropolis algorithm, really, you're walking around a simplicial complex because you're you're walking around the clique complex by adding.
That's right. That's right. That's right.
Can you sort of say something more general about random simplicial complexes and running the Metropolis algorithm? So can you somehow abstract properties that you're using?
This is an excellent question that I did not think about. So no, I'm happy to think about it, but it's a good question. Yeah. I do not know if there's anything very, very general that we can say. I do not know. That's a good question. Other questions?
See, but
Yep.
Gesina has a question in the chat.
Okay.
Are there implications?
Yes.
Detection?
Yeah, so these cliques are related to community. So you could think of them as community in the network, and people
That's
look
right.
at, well, as you know, at community detection and sparse networks. Now, this is not a sparse network.
That's right.
Trying to think what your result means. Is there any implications for community detection?
Right. So I don't. So like you say, this is a problem about community detection. It's just a very different kind of community. It's just like there's one very dense community inside of a less dense community, and there's actually, like I said, there was all of this effort in trying to sort of understand for specific, say, families of algorithms, how hard is it to find hidden clique, and there is a parallel effort taking place right now, doing the same thing for the community detection with sparse community, but as far as I know, there are no reductions, right? So it's like people are doing things in parallel, and some of the results are weaker. So it seems like even though the flavor is similar, the fact that the parameters of it's different regimes of the parameters, as far as I know, there's no formal connections, right? So it's a very good question, and we are all thinking about it all the time. You're like, why can we do what we do, and we cannot, right? So it's somehow you do different analysis. Yeah, excellent question. Thanks.
Thank you.
Question, just to check I'm understanding correctly. So you have the two different bottlenecks for the worst case initialization, and you know from the first one, A, that it's very unlikely that that it will take a long time to get to any clique that has sort of significant intersection with a planted clique. Right. And it's sort of like common sense that if that doesn't happen, then the planted clique can't help you find a bigger clique, but it's somehow common sense, but not.
Right. So there we use Jerrum's analysis, right? So I mean, the failure of Jerrum analysis was just because that if alpha is bigger than a half, I just write here. If alpha is bigger than a half, write in a place that's comfortable. If alpha is bigger than a half, what happens is that most of the mass of cliques is inside a hidden clique, right? And that's not good for you. So we are sort of excluding it. We are only looking at cliques that have intersection at most gamma log n with the hidden clique, right? So actually many of them are completely here. And then we're saying for this kind of cliques, we can, look, so there's one bottleneck here, and it's, it's sort of hard to reach this bottleneck. And inside this bottleneck, we are going to look at the expandable, that's going to define another boundary. And by the fact that we excluded all this clique here, we avoid this problem that Jerrum had with alpha bigger than 1/2. Does that make sense? So we have to repeat it. We have to repeat his analysis. Our analysis does not replace his analysis for proving that you don't find a big clique. Okay, so it's a combined analysis, right?
That makes sense.
Other questions? Okay, so maybe I'll talk a little bit about empty initialization, so starting from empty clique. So I sort of want to give you the picture, and the picture is exactly following on the question that we had right now. Because we are going to start from the empty clique, so the empty clique is somewhere there, there's nothing there, and we want to show that we don't get into trouble, we are only going to look at cliques that are not too big, so our cliques are going to be of size at most 1 + epsilon log n. And we are only going to look at cliques that the clique intersection with the planted clique is small, so it's less than whatever, let me call it just 0.0 log n, right? So, we're going to look only at these cliques. And for these cliques, we want to show that it's going to take us a lot of time. It's going to take us a lot of time to get to the boundary, of these configurations. And I'll tell you what's the main insight is. The main insight is that if the clique is not too large, so if cliques of size, let me call it row log n, for row less than 1, we have the following. So the probability of the size going down, we know. That doesn't depend on anything about the graph, right? So because we just choose a vertex. So the probability that the size of the clique is p minus 1 given xt minus 1, given that xt minus 1 is of size p. So this actually doesn't depend on the configuration on the graph in any way. So this you can compute, this is always the same. It's p over n e to the minus beta. So this is e to the minus beta here. Right, so the probability of going down doesn't depend on the random graph, right? You choose a vertex and it's fixed probability, you know, you only go down the 1 over n or the p over n, you have to choose a vertex inside your clique, and then you have to remove it. This is to e to the minus beta. What's interesting is that in fact, because of the regular structure of random graph, with high probability, we have something similar for small cliques for going up. So the probability that xt,
sorry, you write xt, oh yes.
This is xt, and this is xt here. Sorry, that xt, thank you, that xt is equal to p plus 1, given that xt minus 1, and I know that xt minus 1 is of size p. So you can prove that, say, it's between two constants. So let me write it. What we actually need is just the lower bound. You can prove that this is bigger than 1 over 20 2 to the minus p. But or you can prove that it's of the order 1 over 22 to the minus p, right? So you can prove. So where is the 2 to the minus p coming from? So what's the intuition? If I choose a vertex outside, I want all the edges connecting this vertex to the clique to be n, and the probability that they're connected, you know, to all of them, if we haven't been in a Markov chain and we had memory and so on and so forth, would be exactly 2 to the minus p. But with high probability over the graph, this is always true. Always true means for every configuration of a clique of size p, you know, the chance that you'll move to a clique of size p plus 1 is essentially 2 to the minus p up to some constant. So this means that at least for cliques of small size, going up and going down is very regular, right? So the, you know, going down is completely determined by the size of the clique. Going up, there's some fluctuations, but there are very small fluctuations. So why is this helpful for us, right? So we have the bottleneck set. So let's call gamma the bottleneck set. Or the bottleneck set that we want to reach. So what we want to know is what's the probability that xt is in gamma, given that x0 is the empty set. And essentially what we're going to do is we are going to use reversibility. We are going to say, okay, this is the same. Sorry, this is the same as the sum over all the sigma in omega. The probability that xt is equal to sigma, given that x0 is equal to the empty set. And then reversibility gives you that this is the same as it turned out e to the beta times in omega. All of them are on the same size, so they're all going to be of size p. So it's going to be e to the beta p, and then we get the probability that x0 is equal to the empty set, given that the xt is equal to sigma. Okay, so why is this? So x, I'm not careful here. X t is equal to the empty set, given that x0 is equal to sigma. So we're using the reversibility of the chain. And if you look at this equation, so maybe it's too fast, but if you look at this equation that's over here, if you think of p as small, what you see is when p is small, when you're looking at a small clique, the probability of going down is essentially 1 over n. And the probability of going up is essentially a constant. So if you think about it, you know, I want to go from a clique of size, you know, 0.n log n to a clique of size 0. At the end, I have a very, very strong bias upwards. And the strong bias upwards is stronger than what I paid by the reversibility here. So it's really, really hard to get to the empty set from something of considerable size. If you think about it, it's like a biased random walk. Formally, how we prove it is we compare it to some burst and death process, and that's what gives us the bound in this case. The analysis, there's some numbers. It works well when beta is beta is not of order log n. In which case, the bounds don't work out. Okay, so I think I'll stop here. Maybe I'll take more questions on this aspect, and if there are any other questions.
Elchanan, thank you very much. Do we have any more questions? Actually, I had one question. So, so your result sort of, so I'm just about this sort of root n barrier for planted clique. So,
yep.
I mean, clearly your result sort of removes one piece of evidence that root n is important, or an actual hardness barrier. What do you believe? It's a slightly fluffy question, but what do you believe? Do you think?
So I think actually our result doesn't, I mean, given all the other algorithms that fail, I think that the way I interpret our result is that, just Metropolis is not appropriate for the hidden clique problem. It's not, I don't think it's an indication that the hidden clique problem is easy, right? So I'm like many arrogant mathematicians think that this problem is hard because I tried and I couldn't do it. Right? I try to find hidden cliques, size less than square, and I don't know how to do it, right? So I suspect that, either there's really some nice new mathematics or algorithms that will lead us to find this hidden cliques, which I think would be a breakthrough, or there's real computational hardness here, right? And this kind of computational hardness, there's a bunch of computational hardness problems where, the barrier seems like there are efficient algorithms of the takes times n to the power log n. And I would say that, even for NP-hard problem, we don't have a very good understanding. For these problems, understanding is pretty poor, right? So, it's really just we tried and it fails, and, a little more than that. This stage there's some reduction, but not much more than that. Yeah.
Okay, thank you. Other questions?
Yeah. So back to my question about beta. So I know beta can depend on n, but I mean for a fixed n, you could try tuning beta as like your clique starts growing. Maybe you start adjusting beta. You said that your results hold in that sort of simulated annealing setting. Can you say?
No, so it doesn't hold for simulated annealing. I think it holds for. I have the paper in front of me. So let me make sure. So we tried everything and we proved what we proved. So I think we proved it for simulated tempering. You know what it is?
Yeah.
You know what? Yeah. So I think we proved it for simulated tempering, not for simulated annealing, right? So simulated annealing, the advantage of tempering over annealing is in tempering, there's still a stationary measure, there's still reversibility and so on and so forth, right? So we proved the same result for simulated tempering.
Okay. Yeah, so thank you very much for your talk. Like, I mean, I think that Jerrum's result, I think it's right that this bad initial set that he shows exists is likely beyond the log n barrier. So in some sense, his result is saying, you're already stuck and you continue to be stuck. And so starting at the empty clique is more satisfying, I think. Yeah.
Okay, next. Yeah, I didn't think about this point until now, but I agree that, probably if you sample from this conditional measure, it's above. So yeah, thanks for bringing it up. Thanks.
Okay, so maybe at this point, let me attempt to stop the recording and then we can thank Elchanan.